Got it. Well, good morning, everybody. We're retaping a talk that was given some time ago, and we're here with the famous Children's Cognitive Research Lab to provide some backdrop to retaping this talk. So stay tuned, it's going to be totally fun. There you go. And so my name is Heidi Kloos, and we're talking about exploring links between complexity and knowledge formation. And with me is Michael Droboniku. And he is going to tell us more about the implications for science learning. Something like that. Okay. And we're going to do this kind of back and forth a little bit, and I'm going to start, and I'm starting with this general idea, this general goal that my lab pursues, which has to do with complexity in education. And I put here some pictures of articles that have already created that link between complexity and education. It's exciting. And so you see these four here, and then I have some more, and I'll just ask Michael to add some more. See, there's another one when Davis has done a lot of work. You saw that book that just popped up, more of Mr. Davis. Yep, that's more. And what else do we have here? Yeah, we were interested in seeing also that it has moved into methodological implications, as well as some of our own work on science learning. And there's more, even of people you all might know. I love this last picture that you just see there, complexity in education, from horror to passion, because it just hints at that complexity of complexity science, that complication that comes with it. And so I just thought this title just really very well represents that it really is actually kind of horrific to make this link, but it can turn into a passion if we I suppose do it right. And that's what this talk is about. We're trying to link these fields, complexity and education, in a somewhat more systematic way that potentially can help the field. And as I said, we're going to trade back and forth between Michael and I, but I can't remember now if this is something Michael will talk about or I will talk about. Is it still me?
Yep.
Okay, very good. So this picture that you see here, I love using this a lot because it just shows you how complicated it can get when you start studying complexity. You can see in the middle there are complex systems, and it has to do with self-organization and emergence. That seems pretty easy. But then each of these bubbles have a different kind of system in mind: game theory, evolution, networks. And with each of those comes its own concepts. Now, they're obviously all related, but how they're related, where the overlap is, that's far from clear. It's almost like our field, the complexity science field, is organized into these different pockets, and there's no overlap. So, and actually they're so different. Not only is there not overlap, it's not obvious how that overlap can be accomplished. Like, you see those three pictures that just popped on the screen? There's three different systems, all of which are complex systems. One has to do with how the snow forms, these pattern formations of the snow. And maybe you can't see it right now, but pattern formation was that bottom bubble. And then I took a picture of the forest. Forests, but ecosystems more generally, are also complex systems. And then that famous pot of boiling water that I keep talking about is also a complex system. But if you just take these pictures, it's not just because of red and green and gray, it's just very hard to imagine how they're linked. What does pattern formation have to do with water? Water, and then the forest. So we're trying to, this is the point of this talk, we're trying to, I don't know, not just clean up, but maybe create some common base upon which to build so that we can make that link between complexity and education.
And so the goal of our paper was to identify common complexity constructs that are used in the literature, and then explore the degree to which those constructs could fit processes of knowledge formation. So the picture that we have here provides a visual of that approach. with constructs that make up the field of complexity on the one side, and then processes of knowledge on the other side. And then you can see those arrows that act as the links between the two to show which constructs could map onto what we know about knowledge formation. To begin, though, we wanted to look more closely at the process of knowledge formation. So we focus specifically on children's science learning, which involves the mental activity that takes place in order to make sense of different laws that govern our surroundings. Now, science learning is a large field in its own right, which is shown by this picture here. We can see that there are a number of different domains that fall under the umbrella of science, like molecular biology or physics, chemistry, just to name a few. And science learning is also relevant during preschool. So many researchers and educators look at how children can demonstrate their understanding of science at such a young age, to the point that they even claim that children are born scientists. So that is as if we are born with this capacity or this ability to understand science concepts. And on the other hand, we often see children struggle with science in school. For example, children are known to have misconceptions about science that leads them to making persistent mistakes. And that means that learning science requires not only the accumulation of knowledge, but also a full-blown conceptual change. And needless to say, we're left with many open questions about science learning and how it works. And so the book that we have here in the bottom corner is an example of an edited volume that we've looked at on how to make this kind of learning happen, which they refer to as conceptual change. And that is a different word than learning, because it's focused on almost a relearning of sorts. And incidentally, something we noticed is that the word complex is used in the publication over hundreds of times. So that provides even more of a reason that we wanted to look more closely at what is meant by complexity in the study of knowledge. And to be more concrete about what we mean by science learning, we use a guiding example of children's behavior during a balance beam task that illustrates all of these different points that we presented, that show the difficulty that children have with science learning. And so that is what we're going to discuss next.
Okay, so the balance beam task, we've used that quite a bit in the lab, and it's famous in the literature too, because children sometimes make mistakes. And it starts fairly simple. It's a beam on a fulcrum, and there you see the beam. That's kind of a red thing that goes horizontally, and it sits on that fulcrum and it balances. And the beam can be all kinds of shapes. The first picture was symmetrical, but then you see that second picture, it's not symmetrical. And if you don't balance it quite right, if you try, for example, to balance it in the middle, it will tip. So there's some difficulty of this task. If it's symmetrical, then it balances in its middle. But if it's not, if the weight is not distributed equally, then it no longer balances in the middle. So the belief which kids have that blocks balance in the middle is then incorrect. So therefore, these kids would have difficulty with that bottom beam that you see, their tip. They'll actually have a very hard time balancing that. Even as they see it tip, they might say there's something wrong with the beam. And the argument is that they have this belief that beams or blocks balance in the middle. And for that reason, anything that doesn't needs to be ignored, or there's something wrong with them. So you see here, so eventually they do form a correct belief. So you see here various things that Michael was talking about. They form these beliefs. So they form these knowledge structures and they persist in them. And eventually they change, which is kind of typical of what we see in science more generally.
And from children's performance on this task, we can actually see several truisms, several things that we accept to be true about knowledge formation. So we can use this balance beam example to derive, we ended up with 6 truisms that we're going to go through, but we've categorized them out into different groups. So the first truism pertains to the nature of knowledge, namely that knowledge is organized in some coherent fashion rather than consisting of incoherent pieces. And so in the case of the balance beam task, for example, a child's belief is internally coherent. So they believe that all blocks balance at their middle. Now, the second truism here, labeled B, pertains to the nature of knowledge as well, but namely this time that knowledge may exist in various forms or different types. So we could consider the difference between implicit or explicit knowledge, the differences between superficial versus deep knowledge, or even something like narrow versus more broad knowledge, just to name a few. And so in the case of the balance beam task, a younger child's beliefs about balancing objects might be more superficial than an older child's belief. And there's also research on the task that considers the difference between children with implicit knowledge of how a beam balances versus a child with explicit knowledge on the subject. Now, another truism pertains to the development of knowledge. And here it is generally accepted that knowledge comes into existence holistically rather than in a piecemeal fashion. So for our balance beam example, we can see that children either do or do not have a belief about balancing objects. There's no such thing as a half belief. And our fourth truism, also on the development of knowledge, is that the details of knowledge depend on the context. So that could include the social surrounding, maybe the nature of the task, or even the support being provided as a resource. And there's quite a bit of variability in how children perform in the balancing task. So we often find that the mistaken belief is the most talked about behavior by the child, but there are also other behaviors the child may engage in during the task. So we especially see these when there are changes in the context of the task. For example, a child might try balancing a beam on its side or may start using the beams to play a game maybe, neglecting the thought of their belief that is needed to perform the task correctly. And that could be influenced by the context of the situation. And our next truism pertains to the idea that knowledge persists. In particular, it is well documented that mistaken beliefs will persist. For example, children will famously ignore the behavior of the block that is right in front of them. They could see the block fall and yet continue to make the same mistake because the belief that blocks balance in the middle is something that persists. And finally, we have the truism that conflict can influence conceptual change. So by showing someone their shortcomings of their own belief, they may be more prone to changing that belief or moving beyond the belief in their behavior. And we can see that with the balance beam example in a few ways. For one, the child could see a beam fall when they place it on the fulcrum at its geometric center. And the sight of the block falling could act as a conflict that indicates to the child that their belief is incorrect and needs to be changed. We also see this when a teacher or instructor provides some form of instruction that the block fell and something must be wrong. That could act as a conflict that encourages the child to try something new to get the beam to balance correctly.
Yeah, so before you highlight that, maybe go one step. Yeah, okay. So just to kind of, this was a little dry, and it was pretty much to organize or to describe science learning. So it's like you remember how I showed you the picture of the forest or those snowflakes. This is like us describing the snowflakes, in this case, science learning. So we just came up with 6 of those, and we're going to ask how are they complex, or what do we know about their complexity? And so just to keep track of them, we labeled them so you can remember these 6 things quicker. And so the first one we'll refer to as structure. So knowledge is structure. And then the second one refers to diversity. Knowledge is diverse. And C, there's a holistic construal, and then context dependence and persistence and conflict, or the role of conflict. So this is our description of science knowledge. There might be more descriptions. We just pick these 6 and ask, how are they represented in complexity science? Yeah, so complexity signs anticipate these truisms.
And so our next step was to map out the field of complexity. And so we came up with 12 different constructs, and they're listed here with brief descriptions of what each one is. But while this list isn't entirely comprehensive, it was our chosen starting point because these constructs are often used across most domains of complexity in the literature. So as we mentioned before, it's very rare that we find a universal definition of complexity and see it applied in consistent ways. So part of our first step was to map out complexity, find those consistencies. And so part of our goal here was to come up with a range of different terms that covered different types of systems that we discussed earlier, the non-living systems, living systems, and also thermodynamic systems, just as a way to organize this mapping out process. So here we can see that some of the terms like self-organization, for example, fit the study of all types of systems. So you can see that based on our little X marks at the end of the table. And so that makes sense when we consider that something like self-organization is often considered to be at the heart of complexity. And it's what makes the system complex. And we can also see from the table that other terms only fit the study of one type of system, like affordances. So those are often associated with the idea of agency and the fact that a system's parts can play a role in their environment. And then finally, we have terms that fall under the category of thermodynamics. And those are unique in that they anticipate for the topic of energy transfer that makes thermodynamics so unique. And that said, something interesting that we noticed, how other constructs and complexity also could be used to understand a thermodynamic system and vice versa. So by that, we mean that a thermodynamic construct like autocatakinetics, for example, could be used to study other types of systems if applied correctly, even though that's something that typically is studied within the realm of thermodynamic systems specifically. Now, if we look at this table here, we have our knowledge truisms across the top, and then we have the list of complexity constructs going down the side. So that was the question. How do these terms map on to our truisms of knowledge formation? And to answer that question, we went one by one through each of those complexity constructs, and we used evidence from the existing research to identify whether that given construct did anticipate or did not anticipate each of those categories that we have about knowledge formation. And here's what our results look like.
And I think because we're just retaping this, we're not going to describe each one separately. Somebody can just pause this video and take a look. But we'll do it maybe for self-organization, that idea that systems consist of parts that organize into some pattern of behavior. And you see that fits that idea that knowledge is structured, it organizes itself. And it also fits the idea that knowledge is holistic or construed holistically. And that's why you see those two check marks there. And then you could go through all of these lists, and maybe Michael is just going to, do that. And you can see how each one of them, each idea of complexity maps onto some knowledge truism. And these are just our guesses. Maybe you have other guesses, but this is the way it comes. So we reviewed the literature and came up with this pattern. And whether it's right or wrong is maybe less relevant than kind of the overall pattern. For example, if you just go to the next slide. Yeah, so you see, if you just look at individual knowledge truisms, such as persistence, it's actually anticipated by a few complexity constructs. You see a total of 5 check marks here. And then if you look at the 2 more, the idea of holistic construal and context dependence is also relatively well anticipated by complex systems. But then if you look at the idea of structure or the role of conflict in conceptual change, it's not as prominent. And in fact, the idea of diversity there's one more click. Yeah, diversity, the idea that knowledge is diverse, remember, like it could be implicit or explicit, or it could be deep or superficial. That's not very well anticipated just by one concept in complexity that we found. And so I think we can just go to the summary slide. I forgot now who says this.
Okay, so To summarize our findings from this research, we considered 12 complexity constructs that span the study of 3 different types of complex systems. And then we also considered 6 truisms regarding what is widely accepted about knowledge formation, specifically having to do with the nature of knowledge, the emergence of knowledge, and the change of knowledge. And we found that all complexity concepts could map onto 1 or 2 of our knowledge truisms, which means that each knowledge truism was anticipated by at least 1 complexity construct. And finally, we also found that our truisms of knowledge varied in how well they were anticipated by complexity. So an example that we have is complexity seems to anticipate the persistence of knowledge the best. And in contrast, complexity anticipates the distinction between different types of knowledge the least. And we have the interesting point that conflict that leads to conceptual change can be anticipated by something like our thermodynamic constructs.
Okay. So the next 3 slides are just kind of the discussion of this, and we want to kind of speed this up a little bit because it's the end of our lab time, believe it or not. So I'm just going to run through this a little fast, and you can just pause the video if you made it this far. Some limitations are that, as I already mentioned, these complexity concepts that we picked are arbitrary. Now, we weren't biased, we weren't looking for specific ones. We just kind of skimmed the literature or took pretty much the most prominent ones, and probably we forgot a few. And it's probably incomplete. And similar with the knowledge list, if you maybe come up with a list of knowledge truisms, maybe you'd come up with a different one. So it's also arbitrary and perhaps incomplete. And finally, the mapping, as I said, might not be the same mapping you guys come up with if you were to do it, but it gives you some indications, I think, of where more work is needed. Yeah, so I think we can skip the slide. You can read, it's pretty obvious. And then future directions, and we'll go through fast this one too, if you don't mind. Oh, was I supposed to say something about that? No, okay. Well, I guess we went really fast through it. Future directions, stay tuned. How about that? And for that, we'll just thank you for listening. Yeah? Very good. See you around. Yeah, you can applaud. Great idea.